last time we introduced time series modeling and forecasting, and then we emphasized that before, like we said, that Prof advised that before you carry out or do your mechanistic model, that then it's good for you to do some statistical modeling of your data. It will give you insights on how the data looks like. And then we also said that we mentioned that statistical modeling or statistical modeling depends, is data driven only. Are we not true with this? So maybe you can get from, all right. So it has been sent on WhatsApp, we can check that. So we said why statistical modeling is data driven. Without data, you cannot do statistical modeling, but then mechanistic model, you can still, without the data, you can still gain some insight from the, without doing data, and then you can also add your data to it to be able to make predictions and do all that. So last time we talked about what time series is, that set of observations that are in sequence over time, and then we distinguish between cross-sectional data and and time series data. Who can remind us? What did we say? What's the distinguishing factor? Somebody should remind us between cross-sectional and time series data. Who wants to help us? Let's review. Okay, where is the mic? Somebody here? Or it's not working? Oh. So that others can hear you. Where is this person? Is here.
Collecting data from different places at a point in time.
At a single point. That's what?
Cross-sectional.
Cross-sectional data.
Time series, it will be a regular observation over a period of time.
For a single entity. It could be a single location, and then that's, and then we also looked at various areas of applications of time series. Said time series analysis comes to play in places like climatology, in epidemiology, in economics, in finance, and etc. And then we also looked at some of the steps in time series analysis. And we mentioned that the ultimate goal of time series analysis is what? Who will remind us? What's the ultimate goal? To forecast. You know, man has always had this quest. We want to know what tomorrow holds. What will happen tomorrow? What will happen in the future? And so that's one of the ultimate goal of time series analysis, to be able to forecast, to be able to tell. And then if we know how tomorrow will look like, we can plan for tomorrow. We can make policies that will help us safeguard some of the occurrences that we are expecting tomorrow. So today we'll be looking at stationarity in time series. I remember somebody mentioned it after the lecture that day, that what about stationarity? Stationarity in time series is a very important notion. You know, yesterday, while we were doing, while Dr. Abidemi was taking us through compartmental models, he talked about equilibrium points. Is it not? What are equilibrium points? Who can remind us? Equilibrium points are what? Okay, somebody wants to, what are equilibrium points? What is an equilibrium point? Or what are, yes, who wants to help us? We looked at two types of equilibrium points. We talked about the disease-free equilibrium and then the endemic. So what are equilibrium points? Yes, who wants to help us? Equilibrium points. Okay, somebody is there.
In the system.
When
there's no tendency for change over time.
Thank you very much. There's no change. No change. Say if we have, where's the marker? The S, the T equals, where's, I can't find the marker. Marker. Let us get. So there's no change, say in the susceptible population, the S, the T equals to what? 0. That is the inflow into that class, and then the outflow balances. And there is no increase nor decrease. So we have the S, the T equals to what? This is at equilibrium. There's no change. Now, there is a similar concept in statistics too. there is statistical equilibrium, and that is stationarity, even from the word stationary. What does it mean to be stationary? At a point, at a fixed point, you are not moving, no change. So it's a similar concept, statistical equilibrium, called stationarity. So, and it's an important concept in time series analysis, and that's why we want to look at it today. So the overview, we want to look at what stationarity is, the importance of stationarity, how to check for stationarity, and then we'll look at some of the techniques for making non-stationary time series stationary. And we'll also do some practical example in R. Remember the course is time series modeling and applications in R. So we'll look at a data set, and then we'll see how to, a non-stationary data set, and see how to make it stationary. So what is stationarity? A time series is said to be stationary if its statistical properties do not change over time. The statistical properties of the time series, such as the mean, the variance, they do not change over time. That is, if you look at the time series, you should, if you look at any part, let's say we have, I have a time series here. Okay. So if I see, it's a time series, time here, say maybe malaria cases over time. So if I look at this, any part of this series, I should not be able to, every part should look identically, almost the same. They must be almost identical. Look at this time series. Are they almost identical? If I pick any part, let's say I pick this window, this part, let me call this window, and then another window here. Okay, can we see? Camera, we want you to focus on, okay, is it the marker? Can we get the black marker? Okay. But I think we also need the lights for the camera and all that. So how do we optimize both? Black marker, let's try black marker. Okay. Is it better now? It's still faint. Okay. I think it's getting clearer. Hope I won't fall. Okay. So, okay, I'll try and be careful. Okay. So, if we look at any parts of this time series, they should be almost identical, any parts. So if I pick, say, this part, this is a particular window, and then I pick another part of the time series, and I pick another part. For stationarity, for you to say the time series is stationary, they must be almost identical. Does that apply to this? Huh? It's not. This part is not identical to this, and then you have variations. So the first, we say specifically that what? The mean must be constant. A time series is said to be stationary if its statistical properties do not change over time. And then more precisely, we said a time series is stationary when the mean is constant over time. The mean is what? And that refers to the trend. The trend must be constant. Let's look at this time series, for instance. If I have this, what kind of trend is this? What sort of trend is this? This is an upward trend. The mean is changing as time goes on. The mean is not constant. The mean here, say, is different from if you pick this window, the mean is changing. So the mean is not constant. But we need constant mean for us to be able to make accurate forecast. So for this, the mean is not constant. The mean is changing as time goes on. So stationarity implies that what? We need what? Constant mean. And that is where the trend comes in. And then another point is that what? The variance must also be what? The variance must be what? Constant over time. What is variance? Who wants to help us? What is variance? Variance is what? Square. Square of standard. That is still. What is variance? Who wants to help us? Huh? The variance is what? No cross answer. Somebody should talk. What is variance? Who wants to help us? Nobody is talking here. The difference between a point and a mean, okay, that's close. Variance. Who is helping us again? The average? No, variance is not average. What is variance? Who is helping us? So variance talks about the spread from the mean. If you have a set of values, let's say we have, let's look at, if I have, say 1, 3, 5, 7, 9. What is the meaning of this number? What does it mean? I mean, okay, the mean is what? The mean is 5, is it not? The mean is 5. Mean is 5. Okay. Now let's look at another one. Let's say we have 4, 5, 5, 5, and say 6. What is the meaning of this set of number? Also 5. Huh? Also 5. Now look at these two sets of values. There are some that are closer to the mean, while there are some that are farther. Which one is closer to the mean? The set of values are closer to the first or the second? You see that the first one, the values are closer to the mean. The second one, these values, they are closer to the mean than this guy. So the variance of this guy, this set of points is lower, will be lower. So the closer the values to the mean, the lower the variance. The higher the values to the mean, the spread, how spread it is, then the higher the variance. So the variance for this guy will be what? Higher than what? The variance. So variance talks about the spread, how they spread out to the mean. Now, for our time series, we say that what? The variance must be what? It must be constant over time. As time goes on, our variance must be what? Constant. So let's see this. So if you look at this, we talked about there's a trend here. Now, if you look at the fluctuations. The fluctuations here, for instance, is smaller than the fluctuations here. Is it not? So it shows that the variance is increasing for this particular time series. The variance is not constant over time. And we cannot use this type of data or time series for forecasting because it will not give us reliable output. So what we need to do is to make it stationary. So we said, firstly, the mean must be constant over time. Also, the variance should also be constant over time. That means no periods of increased or decreased volatilities or fluctuations. And also, the auto covariance will depend only on the lag and not on T. So the covariance between two values or two points depends only on how far apart those points are. That means the lag, and not on the actual point itself. So the statistical properties of our time series must be constant over time before we say that time series is stationary. So in general, a stationary time series will have no predictable patterns in the long term. It must not have a predictable pattern like we have there. It must be constant. Time plots will show the series to be roughly horizontal with constant variance. We'll see that later on. That for a stationary time series, the time plot will be roughly horizontal. This guy is not horizontal, is it? It's not. So for a stationary time series, we're going to be having something like this. You see that the trend has been removed. It has been the trend. We don't have that upward trend any longer. And then the variance also will look almost the same, such that if you pick any part of the time series, they look almost identical. That is where we see the what our time series is stationary. So a time series that is not stationary is said to be what? It's said to be non-stationary. Now, importance of stationarity. Most time series data, including epidemiological data, are non-stationary. In fact, most time series data we have in finance, in economics, in climatology, majority of the time series data are non-stationary data. They are non-stationary time series data. Now, however, many statistical forecasting models, such as ARMA. ARMA is a statistical model for forecasting, for making in time series forecast, or the SARIMA, the seasonal ARMA, those models are built on the assumption of stationarity. So if your time series data is not stationary, you'll be having unreliable forecasts. So they are built on the assumption that this data set is stationary. Non-stationary data may lead to unreliable model outputs and inaccurate forecasts. And also stationarity simplifies modeling and forecasting because we have the statistical properties for the time series over time is the same, is constant, is not changing. And so it will make it simplified for forecasting. How do we check for stationarity? If you have your data set, how do you check that this data set is stationary? The first step is what? To visual inspection. You look for what? Look for trends or seasonality in the plots. Look for trend or seasonality in the plot. So this is a time series data of monthly airline passenger numbers in the United States of America between 1949 to 1960. This, the y-axis are in thousands. So if you see 100, it means what? 100,000. And so what do we observe here? Let's look at that plot, the first plot. What's our observation? What are the components of that, of the time series? No chorus answer. Let's hear people out. From here or from here, the people here they've been talking. So let's carry others along. Okay, somebody is over there. What do you observe from the plot, the first plot? What are the time series components of the first plot?
There's a change in variance. It keeps on increasing.
Media, can you give us can we have the plots, the slide now? Okay, am I the one controlling how it shows here? So, yes, can we hear you now, sir?
So I said there's a change in the variance, but in a constant way. Gradually it keeps peaking.
In a constant way. You said
Yes.
there's a change in a...
Like it rises, but steadily.
It rises steadily. Okay,
Yes.
If you look at the first point, you will see that the very first part, the fluctuations or the amplitude around 1950 to 1952 is a bit small. But as time goes on, the height, the amplitude is increasing. Can we see that? And then up to 1960, it's increasing. So it shows that the variance is changing. The variance is not constant for this time series data. And that tells you that this guy is not a stationary data set. The variance is changing. What about the mean? Who will tell us about something about the mean? The mean is not constant. How do we know? Huh? The peak? No. The trend gives us idea of the mean, that the mean is changing. Look at the trend. There's an upward trend. Huh? So if I take maybe a small window between 1949 to 1954, and I calculate the mean, it's going to be different from the mean from, say, 1954 to 1958 will be higher than the mean in the previous. So the mean is changing as time goes on. So this guy has a non-constant mean, non-constant variance. What else do we observe about this data set? What other property do we observe about this data set? Let's look at it carefully. Which other component of time series do we observe here? Cylindrical. We didn't mention that type of...
The pattern is not predictable.
Okay, the pattern is not predictable. There is a particular component. There's a particular time series component that is evident here. Who can see it and tell us? Eh? It is what? No. We are not sure. If you are sure, say it. Okay, you want to help us. Seasonal. There is seasonality there. We can observe some seasonal patterns. Remember, what is seasonality? Systematic peaks. Systematic peaks at regular intervals. We can see some seasonal patterns in that in this data set, in this time series, and it makes sense. So if you look at it carefully, you will see where the seasonal patterns are coming up. Which months of the year do you think we're having the peaks? Which months? Which months? Eh? It's around the center. It's around July and August. There are peaks. Remember, the data is what? Monthly airline passenger numbers. So there is a peak, and that is where most times air travel is highest in the US, around July, August. What happens? There's summer holiday. People travel after they've worked from maybe January till, and then they start traveling, they go for tourism. So there is a high amount of air passenger, whatever there around that time. So we see seasonal peaks. There are peaks around that time. Maybe when we get to the practical session, we'll look at the box plots and see the peak at those months around July and August. So is this guy stationary or not? None, because it has what? Number one, the mean is what? Is not constant. It's changing. What else? The variance is changing, and then there are seasonal patterns there. We don't want seasonality. We don't want predictable trends for our data set. We want it to be constant in time. So it has mean, changing variance, and then seasonal patterns. What about this other guy? There are no clear trends, but then we also have it has some seasonal patterns there, and also some cyclic patterns there too. So this guy is also non-stationary. If you take a particular window, maybe from 1987 to 1990, and then compare it from 1990 to, say, 1993, you see that they are not identical. So one way to check for stationarity is visual inspection, but we cannot always rely on visual inspection. You cannot just say, this is what, you cannot say, this is what I saw. Now they say, before they used to say seeing is believing, Abi. But now it seems it is changing. Seeing is no longer believing. Oh. In the world of AI, there are some things you will see. It is not everything you see now you should believe. Oh. I have seen people believing things. There are AI generated videos of people, and then somebody will just see it and say, I saw that video of that man. And then you want to believe and you start carrying the news. No, you need to also use some other techniques to check, to be sure that this is really true. We cannot just rely on visual inspection. There are other methods of checking stationarity. Another method is the autocorrelation function, the ACF plots. The The ACF plot, maybe later on in the course of this school, Prof will be coming on to talk about the ACF and the PACFs and the likes. So one way you can also check for stationarity of a time series data is to look at the ACF plots. So for a stationary time series, the ACF will drop to 0 relatively quickly. For a stationary, you see the ACF will get to 0. Whereas for non-stationary data, it will decrease or decay slowly at a very slow rate. It will take a long time before it decays to 0. Then we also have other statistical tests. Aside visual inspection or the ACF, we can also use statistical tests to check for stationarity. We have the ADF is the most popular, the augmented Dickey-Fuller test, and then the Kwiatkowski-Phillips-Schmidt-Shinn test, KPSS, and then the Phillips-Perron test. But the first one is the most popular that you can use. We can also do it in our R to check for stationarity. Now, techniques for making non-stationary time series stationary. How do we do it? After you have checked that, oh, this my time series data is not stationary, you need to make it what? Non-stationary, because statistical models like ARMA, SARIMA, they are built on the assumption of stationarity. They cannot give you reliable output, reliable forecast, if your time series data is non-stationary. So we need to see, how do we make non-stationary time series stationary? So we can do that via transformations and differencing. What does transformation do? Transformations help to what? It stabilize the variance of a time series. It will stabilize it. Did we? Okay, remember our first, can we have the slide now again? Okay, so this is what transformations we do. It will stabilize it. Look at the variance is increasing. The fluctuations are increasing over time. So transformation will help us stabilize it such that the variance is no longer increasing. They are constant over time. So transformation helps to stabilize the variance of the time series. If the original time series is given as YT, then you can take log transform. The log transform will now be what? XT will be equals to what? Log of YT. So that will help to stabilize the variance. And then after you've done that, you've gotten your forecast, you can return to the original scale. How do I return? How do I get my YT from that? How do I recover my YT from here? Huh? We didn't hear that too. Huh? Exponential, take the exponent. There is the inverse of log, the exponential function. This guy. Exponential is the inverse of log, the logarithm function. So if I take the log of my time series data, and then I'm done with my analysis and forecast, I can return to the original scale by taking the exponents of. So we can stabilize variance using the log transform. There are also power transformations, such as the square roots and then the cube roots. The power transformation is given as that x of t, xt equals to what? Ytp. If it's square root, so my p will be what? If it's the square root transform, my p will be what? What will my p be? If it is square root transform, my p will be what? 1/2. My p will be 1/2. If I now want to recover the original scale, what do? I will square it. You can take the square root, you will take the square root of your time series data, and then it will help stabilize the variance. And then after you've done your forecast, you can now return to the original scale by squaring. So you use the square root or the cube root transformation. Another one that combines both the log transform and the the power transforms is what? The Box-Cox transformation, and it's given as that. It combines both the log, which is given here, if your lambda, which is the power, is equals to 0, and given as this, which is, but in most cases, we'll be using the log transform for stabilizing our variance. Now, after you stabilize your variance, that's not all. What else do we need to do? We also need to stabilize what? Our mean. We need to, that's trend. We need to stabilize it to make it constant in time. And what do we use in doing that? We use differencing. You stabilize using differencing. Differencing is one of the most common techniques of making a time series stationary. Differencing can help stabilize the mean of a time series by removing changes in the level of a time series and therefore eliminating or reducing trend and seasonality. So differencing helps to remove the trend. It also helps to remove the seasonality. It make it almost horizontal, or is almost an horizontal. So differencing computes the difference between two consecutive observations. So if I have observation yt minus 1, observation yt, say if we have let's look at it. So if we have some observations, say I have my time here, maybe this is January, and then I have 5 February, say I have 6 March, say I have 100. So differencing, so will give me what? So I'm going to do what? This guy minus what? 6 minus 5 gives me what? 1. And then I do also 100 minus 6 gives me 1 what? 94. So this is going to be the difference. 1 sorry. I was thinking it's 200. So we have 94 here. So this is a differenced data set now. So this guy has been differenced. And then in R, you use the difference function. When we get to that part, so we're going to see how to do that in R. So differencing compute the difference between two consecutive observations, yt minus 1. Media, the slide. Is it there now? Okay, where there is a difference at time t between the series at point yt and yt minus 1. Now, in some cases, differencing once is not enough to produce the required stationary series. So if you carry out differencing once, you might not attain stationarity. So you need to also what? Do second order differencing. You difference the second time. And in most cases, second order differencing is sufficient for stationarity. Is that clear? So we difference once, and then you can check using any of the statistical techniques to check if your data set is now stationary. If it is not, you difference again. And like we said, most times, second order differencing is sufficient to make a series stationary. So those are the two steps in if we want to make our non-stationary data stationary. So let's now see some of these things in R. Let's put on our system and go to our R so that we'll see how we see a non-stationary data and see how to the process of making it non-stationary. Can we do that now? Let's go to our R. Let's go to our R Studio. Open your R Studio. Your R Studio. Have we opened our R studio? Okay, let's wait. If you are not there, say wait for me. Okay, we'll wait for you. Are we together now? How many seconds more should be added? Huh? 2 seconds. 60 seconds. 180 seconds. 3 minutes. So we'll find the mean of all those values. And then we'll just pick that. Okay, so let's get our R studio ready. You know, yesterday in our Mr. Idowu took us through some of the functions and all that, and we learned that there are inbuilt data sets in R. How do we call those things? What's the function for you getting that? Who remembers? No, not demo. To get the inbuilt data sets. Data, the data function. The data will help us. So let's go to our arrow and type data. There's a data there. Let me increase this guy. Can we see it now? Okay, so data, have you typed that? Then you run it. Who's saying something? Okay, your R is still loading. Should we wait for your R? All right, so let's wait for some R's. Because of some systems are not the same. So let's wait for some R's so that we can carry everybody together. We can go along. So if you have your data, you can run it so that it gives us yes, just this way, and then run, Control Enter, or you run to give you the list of inbuilt data sets in base R. These data sets are already in R. You can call them or use them as you like. They are inbuilt in base R. Are we still waiting for R to come up? So, okay, let's wait 2 more seconds. Alpha, it's still coming up. Okay, maybe you check your neighbors. Sir, is your R okay? So let's run it to see some of the data sets, the inbuilt data sets in R. Have you done that? So you see the data sets, the list of data sets in R, inbuilt ones. The first one is what? Air passenger. So that's what we'll be using. Yes? Please, ICAMMDA team, let's help out. Let's help out. Let's go around and I should give you data from epidemiology. Yeah, you will get there. So this is just to explain. Don't worry, it's a course, Mr. Caputo. Calm down. You get data from epidemiology. So this is just a way of helping us to see how we can make use of data sets that we have in. So in course of time, hello, sir, Mr. Idowu. In the course of time, we'll get real data, malaria data to use in our analysis and all that. So, has everybody seen the inbuilt data set? So the first one, air passengers, monthly airline passenger numbers from 1949 to what? 1960. So let's go back to our R script. You have not seen. Please see. Who is helping? Just data. Okay, if you need help, please raise your hand so that somebody can help you. If you need help, just data. Data function, and then you run it. Just run this guy. You don't have what? I didn't hear that. Oh, you don't have air passengers. Ah, that's interesting. What could be the problem? What could be the issue? Mr. Sam. You have seen it. Ah, okay, thank God. So have you all seen the air passengers? So that's what we want to use. We want to use that data set that is inbuilt in R, the air passengers data set. So let's type air passengers. Air passengers. Take note that, remember that R is case sensitive. The A is in capitals, and then the P is also capital. A is in capital letter, P is also in capital letter. So let's take note. That's how the data set, the form in which the data set came in. Air passengers. Air passengers in R. Are we there now? Okay. So can we run it? To see, you can run it. Place your cursor where, and then you run Control Enter. Is it done? You can check your console to see some of those values from January 1949 to what time? Aha, from January 1949, we can see in thousands. So that's the air passengers. It's in, but those the values, but I'm telling you that they are in thousands, but they are just, they've rescaled them to just them. So that's the air passengers. Okay, so let's take this data set and assign it to a particular variable. This air passengers data set, let's assign it to a variable. So I put data, let me call it data 1, and are you seeing this? So I've assigned my air passengers to data 1. Can we do that now? Or you can call it any name. If you don't like data 1, you can give it any name you want. Yes, I just went back to the same line. I went up. And that's what we'll be using. So go use data 1 so that there won't be confusion. So let's use data 1. Data subscript 1. Air passengers is being assigned to that variable now. Data subscript 1. Have we done that? Is there anybody confused? If you need, no, just we are not to get any value. Have we done that? The first one. Somebody should help her run it. So assign air passengers to data 1, and then you can run it. Run it if you have done that assignment. Run it. You can run it. Have we done that? So you see the air passenger, it's now stored. So we can now, you can type data 1 now so that we can view it. And then we see the same thing there. Okay, have we done that? Air passengers assigned to data 1. So let's plot this time series data using the plot function. Plot plot data 1. Are we together? Please, if you are not following, just raise your hand. If you have any issue, let people help you. So let's use the plot function, plot data 1. Are we there? So what should we put in our, let's put the title. The title. What's the title of the data set? Air passengers. Maybe monthly air. Main is the title. It will give us, we want to plot air passenger. So you will see the output. Okay, maybe what we'll do is, maybe we shouldn't put main first. And then let's run it. Okay, we are learning. So the main, we give you, you have your plot, the title. When you see the output, you will see it, what you have typed. So monthly air, maybe air passengers number. From what time? 1949 to 1960. Yes, main equals that. Monthly air passengers number from 1949 to 1960. Okay, you said my 1960? Okay. Oh, thank you, ma. 1960. Are we there? So let me come to the next line. Are we together? No, I'm still. So we've put the main, the title. Now I want us to label the x-axis and the y-axis. The x-axis and the what? We have our y-axis. The x-axis. What's in the x-axis? Time. In years. 1949, 1950. So let's label it time. So use X lab equals to this guy. Yes, you can go to enter, put comma, and then click enter. So let's call this guy time. After your 1960, let me go back. See it. There's a comma here. After the main, you put a comma and then, oh, thank you very much. Thank you. No, okay, we are not done now. So we are still, okay, maybe let's just close it and everything will be inside. Let's close the brackets. And then let's put everything inside. So our X lab is what? Time. What about the y-axis? What are we calling the y-axis? The name. Maybe number of passengers. Number of passengers. Number of passengers, in this case, in thousands. You can open a bracket in thousands. In thousands. Number of passengers in thousands. Number of passengers in thousands. The beginning. The time. The Y lab. Number of passengers in thousands. Are we there now? Okay, obstructing. Which one am I obstructing? This guy. So I think let's run it and see. Let's run and see the output first. You said? Let's run and see. make sure your brackets, all the brackets you have there, they are even numbers. If you have odd numbers of brackets, there will be issues. So let's run it. Let's plot. You run. So can we see that? You can zoom it to see it very well. You can zoom. You can zoom. Can we see this? The monthly air passengers number, and then that's the y-axis. Can we see that? Have we gotten that plot? Who has not gotten it? Who has not gotten the plots? We need help. Oh, ICAMMDA team, let's help out. Can somebody help Daddy here? Someone is raising up his hand here. The code, and that's why I'm showing it. Have you gotten that? Prof, ma, have you gotten? All right. So let's wait for others. Let's wait for others. If you have gotten that, you can put color. The default there is black. You can add color to it. You can add color to the plot. Put col equals, let's say blue. You can add color. You can add color to your plots. The default is black. Now, and outside we saw a black color. So you can add color blue or red or whatever color, your favorite color. We should. I didn't hear you. You can add color and run and see that the color has changed from black to blue. Yes, you can. We'll look at that later. We are concerned with the plots now. Don't worry, Mr. Sam, and we're still coming to look at visualize. So maybe let's just look at the plot for now. Are we together? Do we have our plots already? Okay. Which space? In the space. In what way? I don't understand. What happened? That I did not start. No. It's just by default. Once you press enter, Just press enter to go to the next line. It doesn't matter. So we have this, our time series data. Are we together now? Okay, let's give 1 minute more for those that are still having issues. Red color. This man likes red. Says red is his favorite color. So look at our time series data. It's clearly non-stationary, is it not? It's a non-stationary time series data because we've seen it earlier. We have seen all the properties, statistical properties, that the mean is changing, the variance is changing. It also has seasonality. Okay, let's see. I promise that we are going to see the seasonal. We can use box plots. Let's see box plots to see data 1, data 1, tilde operator, and then we use the circle function to get the box plots. The tilde is on your system. The tilde ups. Can somebody help her get tilde? The tilde operator. Okay. So data 1. Remember, data 1 is our air passengers. So we can get the box plots to help us see the seasonality. And then I can run it. So from the box plot helps us to, shows us the peaks. Can we see which month here shows the peaks here? The 7th month and the what? 8th month, July and August. So it shows seasonal patterns that every year from 1949. So what the box plot does is all the Januaries, it grouped them together, the Februaries, the March, from January to December, and then it grouped them. And then here we now see that the peaks, there are peaks in air passenger travel around July and what? August, the 7th and the 8th months. That's where the peaks. So every year we have systematic peaks at those points. There is a whole lot of traffic around that period. So the box plot helps us to see that. Now, are we together? So let's now carry out transformation on our data sets. Remember, transformation is the first technique. What does transformation do? Who will remind us? What does transformation do? It helps us to what? It stabilizes the variance, the fluctuations. Transformations helps to stabilize the variance. So let us go. Let me call it data 2. Okay. Maybe did you check the code correctly? Have you run data 1 earlier? So let's log transform data 1 now. Remember, data 1 is our air passenger, it's our original time series data. So let's assign that to data 2. We want to log transform the original data set, which is data 1. So we use the log function, and then we assign it to data 2. Are we there? Okay, let's wait. Yes. Okay, let's wait. Let's carry everyone along. Yes, sir. Number 7, we want to, our original data set is data 1. We have assigned to data 1 now. So we want to log transform. Remember we said in stationarity, in transforming or converting non-stationary data set to stationary, we need to what? Carry out transformation to help us stabilize the variance. The fluctuations that are increasing, we want to make it stable. So that is what, so we are using the log transform here. That's the log function, the natural log. Log, L-O-G of data 1. So we can run it. We can run it. And then let's now plot it. Plot, if you have run it, you can plot. Let's plot it. Plot data 2, beautiful. Plot data 2. You can, okay, we might leave, let's just put color. Let's put color as blue. We are here. Who is lost? Okay, let's wait for people that are behind. Some persons need help over here. Please, can we come to help them? If you need help, please raise your hand, wave. Sir. So we want to plot the log transformed data sets. It has been transformed. We have and assigned to data 2. So let's plot it. We color it blue. So let me do that. Are we together? Have we run the plot? Okay. Box plot, okay, to help us to show the seasonal patterns, the seasonality. And then you saw from the plot, from that box plot, that July and August has the peak. There are peaks in July, they have the highest this thing there. So it helps us, it shows us seasonal patterns in the data sets. I'm not the one that put it though. Which sign? Okay, the tilde. Tilde is an operator tilde. All right, so can we zoom our transformed data now? The plot, let's zoom it and see clearly. Have we done that? What do we observe here now? What do we observe? The fluctuations have been what? Stabilized. Can you see it? They are almost the same now. The variance is being stabilized by log transforming it. Can we see? Somebody says he cannot see. Please see the variance. Maybe you compare with the previous. Let's go back to the previous so that we can see the transformation that has happened. This is the previous. Check this. Can you see the previous now? This is the original data set. See the variance between from 1949, the fluctuations is quite slow. And then as we increase in time, the fluctuations are going higher, it's increasing. So, but the transformed, the log transformed. Let's see the log transformed now. You can see the difference now. The variance has been stabilized. The variance has been stabilized. There are no ups and downs and ups and downs. So that's the first step in our stationarity, in carrying out stationarity. Okay, how can we? I didn't get the question. No. All right, let's wait for you. Put what? And you can put it, you already know it. I don't want us to waste time on all those. So at your spare time, you can put the title, main. You can even increase the length width. You can use LWD and increase it. But that's not length width equals to, let's say, 3. You can increase the width. You see the thickness, the width of the line. You can increase it as you like. Let me put it at 2. So there are many things you can do on that. We'll see talk about all those ones later. Okay. Length width equals to 2. That's the width of the line width rather, not length width. Line width. LWD equals to 2. So it will increase the thickness of the line. Can we move on now? So we have log transformed to stabilize the variance. But is our time series stationary yet? It's still not stationary. What do we still have there? We can see what? There are still upward trends. The mean is still changing. Even though the variance is now stabilized, but the mean is still changing with respect to time. It's increasing. So we want to stabilize the mean now. How do we stabilize the mean? We do what? Differencing. We difference to stabilize the mean. So let's stabilize the mean. LWD, line width, the width of this line, of the line of the plots. Line width, LWD. Are we together? All right, so let's data what now? Data 3 will be our, so we difference, use the difference function, diff, diff, diff will help us to difference. What are we going to put there? What are we differencing? Data what? Data 2. Don't go and difference data 1. No. Remember, we've already log transformed. So we are following it. You are doing that on the log transformed data set. So we have log transformed that. So we have data 2. Data 2. So difference, we want to carry out differencing. 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 So if you have done that, you can run. You can run it. And then let's now plot it. After you run, you plot. You plot. So I plot data 3. Data 3. Data 3. What else do I need? Let me put color. I think I like color blue. So you can use color favorites. So plot data 3, color blue, let me use my line width 2. Line width 2. And then run the plot. Run it. Have you done that? Can we see the output? Data 3. Yeah. Huh? I didn't hear you. You are feeling like an R specialist. That's good. So we can zoom it so that we can see it clearly. So we've done differencing now. What does differencing do again? It helps to what? It stabilizes the what? So there are no more trends there. We have stabilized the mean. The time series is roughly horizontal now. We don't have changing mean. So if you look at, take any part of this time series plot, they will look identically the same. That is the aim. Is that clear now? So we have carried out, we log transformed to stabilize the variance, and then we also stabilize the mean. The mean. Yes, sir. The what? Okay. Yeah, you see that they are closely identical. It will not be exactly, but then you see, so it could be that maybe you still need to do differencing again. Yes. How do you do it in modeling or what? Yeah. So what we are saying is there are no changing. The statistical properties now, they are constantly the same. The mean, the variance, they are not changing as time goes on. That's what it just means. It means there. So there are no statistical properties that we mentioned earlier for non-stationary that are changing as time goes on are now roughly horizontal and then the same. So we can also, now we may have to do, there are also statistical tests that you can carry out, but it will require us to install some packages, and so maybe we can do that at our leisure time, or maybe when Prof comes, he's going to put us through how to do that. For instance, the ADF test will require the some package like the T-series and all that, and we don't have that time here. But let's look at the ACF plots. Yes. 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 Okay. Okay, yes, you can put your comment. For instance, for this box plots, thank you very much for that. You can put to show seasonality. To show seasonality or seasonal patterns. To show seasonal, you can comment out for the box plots to show seasonal or seasonality or seasonal patterns. Then for this, you can put log transform to maybe stabilize the variance, so that when you are going over your code again, you can understand what is happening. Thank you very much. So log transform to stabilize variance. To stabilize variance. hashtag log transform to stabilize variance. Then this guy, line 9, differencing to do what? To stabilize mean. To stabilize mean. To stabilize the mean. Differencing to stabilize mean. Then we can also, so let's look at the ACF plot, the autocorrelation function plot for, okay, differencing to stabilize mean. Differencing to stabilize mean. So let's see the ACF plots for data 1, that means the non-stationary data, and then the ACF plot for the stationary data. Remember we said for, yes, function. Remember we said, remember that in time series, we are looking at how to make future forecasts. Our future forecast depends on past or previous events, previous observations. So that's where, so we want to look at the correlation between past observations and then the current observations. So you can check the ACF plots for data 1 now, for the non-stationary data. So if we do that, so you can run this, the ACF, and then the ACF of data 3, the stationary one. So my time is up, Abi. We have, they say our time, we have shot 18 minutes past. So, who should be patient? Okay, so ACF of the original data set that is non-stationary, and then the ACF of the stationary one. Autocorrelation function. We are looking at the correlation between the current observation at a particular time and its past values, the lagged values. So we said for non-stationary data, the autocorrelation values, they get to 0 slowly. And that's what we are seeing here. If you can increase the lag value, maybe if we use lag dot max, it will increase. So if we run for the stationary one, you will see, you see this, you see the difference between the ACF of the non-stationary time series and then the one for the stationary. Maybe when Prof comes to continue, is going to tell us more on ACF and ACF of and PACF. Okay, so my time is up. Thank you very much. We'll see.